treated with oxygen. And then they have 3 clarifiers. You'll see there's 1 large and 2 smaller ones. So once the activated sludge has been treated, it then has to sit in the clarifier, settle, and then we get our nice clear effluent on for its move on to its next phase of treatment. What we can do with the AGS or Narada technology is we can achieve extremely good settlement with these granules. So you'll see this image on the right. We have granules on the left and then a conventional activated sludge on the right. And this is a settlement test, and I think this is after something like 5 or 10 minutes. You see the granules will settle and compact to an incredibly dense flock, whereas on the right is conventional one. And this conventional one, it'll give it 30 minutes, it's going to settle much better, and you'll probably have like about 1/3 of that jar would have the kind of brown biomass in the bottom, and the top would be clear. But these granules, the way they can settle, obviously aid of gravity and the nature of the granules, so much faster. This allows us to have significantly smaller reactors. We don't need the clarifiers anymore because we can use a reactor in a sequence batch process to be able to treat and settle in the reactors. And we can also run at a much higher concentration as well. So that in a conventional plant, that biomass spread out everywhere, the granules are much more dense, and we can pump in a lot more sewage essentially to treat. So all in all, that gives us, like they used at Foley, Alabama, we had this old plant I was mentioning, that's a 2 MGD facility. The Narada AGS technology was able to use 3 different reactors with some associated side stream equipment into pretty much half the space, and they got up to 3.5 MGD of capacity through that. So huge footprint saving, which is really beneficial for us, especially Robert mentioned on his earlier slides with how expensive land is and how tight and small the spaces we need to use. So a huge advantage for the city of Marble Falls. The second point is the water quality we'll get from the AGS treatment system. So when compared to conventional activated sludge, that process does not allow us to biologically remove nutrients such as phosphorus, nitrogen, which was on that table that Robert showed you. The AGS facility, the AGS technology, because we can grow these granules and we can essentially perform different, we can have those different environments, right? We can have the anoxic zones, we can have the aerobic zones, we can have the anaerobic zones all within one granule. We can symbiotically encourage these microorganisms to treat water to all those different standards and uptake all these nutrients, which is hugely beneficial. And you can do that with without the AGS technology, but you need even more space, even more reactors, and even more cost. So this will really help the city moving forward to achieve these higher these higher effluent goals from the treatment plant. Before then, we need to go ahead and do our advanced treatment on the back end of that. So a couple of specifics on this slide for some of the design features that we're moving forward with for our detailed design. As with any sequence batch reaction process, we also have the option to equalize flow up front of the treatment processes. This allows us to downsize our reactors behind the equalization basin. So Plummer with the city and with the equipment supplier really looked at, okay, do we have one EQ basin and 3 slightly larger reactors, or do we have 4 much smaller basins? Plummer did a detailed 20-year life cycle costs of comparing these different options for design. The things we looked at were relifting. Now, if we have an EQ basin, we can flow by gravity into the EQ basin, but then we've got to lift it out of that EQ basin into the reactors. EQ basins, well, they don't have a ton of treatment equipment in them. They still need to mix and make sure we're getting a good, even and non-septic conditions for the raw feed. After this analysis, we figured out that the capital costs alone were cheaper with the EQ basin and the 3 basin setup, just because we don't have all the specialist equipment inside the reactors. We only have 3 reactors. And in terms of life cycle costs over the full 20 years, it also worked out much cheaper. So this is what we recommended to the city and what we move forward with, the EQ basin and the 3 reactor design. The other key part of our design was to minimize footprint even further. we decided to go with the rectangular basins. If you remember on the previous slide showing the Foley, Alabama facility, they had those 3 circular reactors. What we're doing is going to be much more similar to this other project I have up on the screen here, the Narrator facility in Walcott in Kansas. Now, this was a really, really tight footprint. You can see the land up there they don't own. This isn't just a sliver of land. They put a ton of treatment stuff in. We're not quite that tight bounded at Marble Falls, but we're much more, much closer to buffer zones and some unusable kind of areas to construct on. So we're pretty confident that we would save some costs and save a lot of footprint by going ahead with the rectangular basin design. Should point out these little kind of catway walkways in between. That's the shared walls of each reactor. So there's 3 reactors you can see on that image. The other thing with our design that we feel is pretty neat is this utilizes EQ basins. So we were able to size the EQ basin exactly the same as the other reactors. This allows the city in the future to dismantle the relift pumps and the mixing equipment in it and put all the treatment equipment into that reactor, and they'll gain almost another megagallon a day of treatment. So that will save the city a lot in, down the line. Construction costs are always going to be cheaper today than they will be in 10 or 15 years time. And the final kind of design feature we went with was we did some pretty clever pumping and valving arrangements to allow the city to either feed these reactors by gravity or pump flow. It'll also help them convert that EQ basin in the future much more efficiently with less downtime and hopefully less expense. So some of the design challenges we faced as a design firm with this proprietary kind of new technology in the state of Texas was, how do we quantify that the manufacturer is being able to deliver what they say they'll deliver? Process engineers, we do this, well, initially we did this through process modeling. Most process models now actually come with like an AGS. They have a built-in AGS packet because it's coming so common. And this little screenshot here is a little bit blurry, but it's an output from we use a modeling process called Sumo modeling. You can see here we have the equalization basin, we have our reactors, we can plug in all the flows, expected effluent input and expected effluent output qualities, as well as modeling some side stream processes such as decant, supinate, and return flows. These are pretty key. And we were able to successfully get our model into steady state, into balance, and our numbers matched up really well with what we're being told from the manufacturer. So that felt very good for us early on in the project as design engineers. Secondly, we did a couple of we had a bit of a different approach to chemical addition. I won't get into this too much, but essentially in most biological nutrient removal processes, you typically design a chemical backup, particularly for meeting things like phosphorus. For us, in the first stage of this project, before we had to worry about advanced treatment, being able to reliably meet a very low phosphorus limit wasn't something we had to worry about. So we were able to save the city a bit of cost in this first phase by designing in such a way chemical addition could be added at a later date and save a lot of money as well. Just keeping a ton of chemical on hand that they likely were never going to use was pretty beneficial. Some of the other challenges were the existing plan that Robert mentioned in the flood zone. It didn't have great flow data or flow monitoring. So this is something we'll correct in the new, or will improve in the new expansion project. But what that does leave us means we don't really have a good understanding of the diurnal flow. We don't understand how much flow is coming in at what time of day, and each wastewater treatment plant really all over the world has a kind of unique thumbprint, of what kind of flows they see. This probably led us to having to design our EQ basin slightly more conservatively, because we just didn't fully understand what kind of flows would be coming in. But in the future, going forward, for the next expansion, we hope we could potentially downrate or uprate treatment processes accordingly. Some internal process flows, head losses, and hydraulics when we were figuring out our piping and different side stream treatment basins was a big challenge, mainly because we're working with a proprietary manufacturer's technology. So me as the technical lead, I didn't know what I didn't know. So it was all about trying to ask the right people the right questions. We had some great support from a sub-consultant engineer who'd just gone through this process in Colorado, Idaho Springs, which was super beneficial, really helpful. And the equipment manufacturers were very helpful as well, answering our questions and kind of putting us at ease. And finally, just any design challenge on a project when you're talking about multidisciplines. So we have structural engineers, you have process engineers, you have mechanical, we have electrical, and then we have this other group who are providing the treatment within these little reactors. You can kind of see the shape of these rectangular basins in this conceptual rendering that Plummer provided. The supplier was doing everything inside the basin, and we were doing everything outside the basin and then some stuff inside the basin. So using 3D modeling is just a really helpful tool that in general most design engineers use on projects, pretty common, but for us it was very beneficial in this project. So just to do a brief kind of overview on some of the other things we were doing, not specific to the AGS technology, you can see our detailed design. This is probably now 60 to 90% drawing set now, so the locations are pretty accurate to what we hope will get constructed. We also had to design a new lift station of the existing plant that Robert mentioned in his presentation, the flood zone. We still have to move all the effluent that was going to that site 3 miles north pretty much to our new site. So that's a pretty big structure. We also wanted to size the pipes accordingly so that when they do grow, we can still convey that effluent as needed up to the new site. We have to then demolish and restore the site for the treatment equipment we don't need. That was also part of our design. I mentioned the force main. We also needed to then connect this new facility to the purple pipe, the reuse equipment we were talking about earlier, to be able to do that irrigation to golf courses and public park facilities. So we had to then, we're also going to have to design another pipe going all the way back towards the city. So a lot of conveyance as well with this treatment plant project. And then finally, the next phase, once we've designed and constructed the treatment plant, will be to start pilot studying and doing some more data analysis for the DPR project. Yeah. Checking I'm good on time. So with this new technology, a big challenge for us was permitting it. We've worked pretty closely with the TCQ on a number of projects as design engineers. We're not new to, Plummer as a firm are not new to permitting and designing new technology. And this one was no different. So we had a lot of discussions and workshops with some key folks at the TCQ. On this project, they really saw it. They initially just really looked at the fact that we were a Texas land application. So we didn't really have these real stringent effluent limits. So that definitely helped the TCQ kind of be comfortable and come to familiar with the technology. As Robert mentioned before, we have these effluent ponds, we have reuse, we have plenty of ways where we can push this effluent if it was non-conforming. So that definitely helped. We also have, we're also designing filtration cloth media filters on the back end of this treatment process. So that to meet this type 1 standard we referenced earlier, that also helped the TCQ have much more confidence in our design and in the technology. So the TCQ anticipates us also submitting data from the Foley, Alabama site that I had up on the slide earlier. Typically with new technologies, the TCQ can require you to do a pilot scale study to prove the technology works. But for us, we were able to save a lot of time by agreeing with TCQ that we could submit just the data that's coming back from Foley, Alabama, somewhere there's a similar-ish climate to Central Texas. The other thing TCQ agreed to was they wouldn't require a performance bond for this technology, which was good for the manufacturer and the supplier. And they'd be willing to approve this as innovative technology when we submit plan specifications and we request such a variance. So we alluded to earlier, we're currently actually between 60 and 90% design. We have a CMA or construction manager at risk selected that's helping us review our plans and helping us review the city constructability items. And they'll hopefully start bidding out some of the early lead equipment packages potentially this summer. Actually, Robert, would you mind talking through the final funding slide? Robert knows a little bit more than me about the funding side of things, but we're also working through some of the funding, and I'll let Robert update you on that.
Yeah, it's kind of interesting. It's been a challenge. City of Marble Falls is not that large of a city, and taking an existing treatment plant, shutting it down, restoring the site, moving the effluent 3 miles north and building a completely new facility, as you can imagine, that's an expensive proposition. Well, early on, they submitted an application to the Economic Development Administration and got a grant for about $3.25 million or 3.125 to cover some of the environmental documentation, as well as the preliminary and design engineering elements of the project, and several other pieces as well that were needed. Planning for the wastewater system, developing a model. Well, when you develop a model, that means you've got to have all the field data on all the manholes and collection systems so that you can build the model. And I'm looking at Kerry Johnson back there because he was working for us and he helped accumulate a lot of that data that went into developing the wastewater model. So that's how that initial grant was expended. Also, a lot of the evaluation of effluent management alternatives and strategies was incorporated into that grant funding. But then through the Water Development Board, fairly unique, they got a flood infrastructure fund. It's considered a loan with forgiveness. So they got about 16 million in loan and 13 million in loan forgiveness. So that gives them almost $30 million for construction of the initial 1.5 MGD of capacity, the new lift station and the new force main to take the effluent up there. They also applied for a Clean Water State Revolving Fund for basically taking the plant from 1.5 to 3 million capacity. And that's really about another almost $10 million. And then a Clean Water State Revolving Fund loan with forgiveness for expansion of their purple pipe system. So total loans and loan forgiveness, you can see we're at about 46 million in total funding, and that's still probably about 20 million or so short of what the project is going to cost. So one of our challenges as consultant is to try to work with them to continue to look at other funding strategies as this project moves forward, and even as we move into looking at the advanced treatment for the DPR component. Fortunately, the Bureau of Reclamation and some other federal sources provide good funding for those kinds of elements, and that's kind of down the road yet to be determined, but that is the track the city is on and committed to for One Water Marble Falls. So questions for Perran or I? Yes, sir.
Forgiveness, is that related to green infrastructure?
Partially related to green infrastructure, yes. Part of it's green infrastructure, part of it is economic within the city of Marble Falls. They have a fairly large segment of their population that's economically depressed. So, but it's both. So, yes, in the back.
Yeah, you mentioned 3D modeling for some of the space planning. Can you talk about what programs you use?
Yeah, so our structural engineer, we have a structural engineering sub actually, so we don't do that at Plummer. They use Revit models, I believe. And then mechanical at Plummer, we typically do AutoCAD or CAD 3D. So I think we now use a sharing platform, BIM 360. You're familiar with that, which is kind of like a cloud-based platform, which is pretty good because all the models are live on there. So the structural engineers working on something in Revit. Again, I'm not familiar with how they convert that exactly, because I know they use like surfaces and points is a little bit different to, definitely not my wheelhouse. You can probably tell talking about it. Kerry is laughing right now because he knows that stuff more than I do. But the cloud-based platform is super good because structural can just, it refreshes so many times a day, I think. So if they make changes and we're putting some mechanical equipment in there, we can say, hey, wait a second, this top of slab is at a different elevation, or our piping needs to penetrate through something. So there's a ton of stuff you can kind of figure out with that. To answer your question.
There would be an innovative technology for TCQ, so that would be added to their list of innovative technologies. Other municipalities would then be able to do this, or would they have to go through a similar process?
That's a very good question. So really everything TCQ is built on the 217 guidelines for what we do in wastewater treatment. So until the TCQ adopt guidelines and write it in there, it doesn't become like a regular technology. So on this project, I should have probably mentioned that on the bullet points, is they're kind of permitting and reviewing it as a standalone project. Now, it definitely helps if we go ahead and construct this and it performs well and TCQ see the data. But, if we were to do another project or another client or another firm was to do it, start it a couple of years' time, they'd still have to do the same approach. They still have to go to TCQ, show them information, hopefully get around not having to do a pilot study if they so choose, if that makes sense. But yes, until they write into regulations, that can take, to get a TCU to update guidelines is not a fast process exactly. So it could be a while off.
They're in an update cycle right now
Yes, we
for
missed
the
that one.
217 regs, but this is of course not incorporated in that update. Yes, Sam?
When do you expect the plans to come online and subsequently the deep drawings on it?
Okay. If we get started this summer, like we're planning to, we're hoping that the plant will be online by late 2025. And the TCQ drinking water staff treats direct potable reuse as if you're developing a new raw water source. And so they require basically a year of testing to characterize the raw water source. So what that means is if the plant comes online in late 2025, and we take 3 months or so to get the granules formed and get it fully functional, then we're probably into the first quarter of 2026. A year of testing brings us to the first quarter of 2027. And then we've got to get design and construction of the advanced treatment online. So that's probably another 2 to 3 years to get the design and construction of the advanced treatment facility. So we're probably looking at 2030. And I hope you're not looking at me saying that guy looks old. He's not going to be around, but you might be right. I don't know.
Which is why, Robert showing those like graph early on with the bar hitting. It's like, yes, we're starting this phase pretty early and they're comfortable, but 2030 comes around and they, if we're up at 3 MGD and we only have 2 MGD of disposal available to us, that's a tricky situation to be in. So yeah, time is key. We can't mess around now.
We were talking about how there's different treatment levels within the reactor. Is it within the reactor, or is it just the total effluent? And how are you going to differentiate between those? Whether it's the just straight effluent that's going to your land application, whether it's going to your purple pop or to eventually the TPR?
Yeah, that's a good question. So the city of Marble Falls is something we discussed with them kind of early on. It's like, hey, you could save a lot of money if we're like, downsizing, we're treating to different essentially effluent standards. But because it's not a huge site at 3 MGD, the city felt that it's just going to be so much easier to have one water quality and meet that higher quality objective. And like Robert said early on, yes, you're probably paying, per dollar per gallon of water treated, you're paying a higher rate. But for operators, I think it's much easier to be like, this is what you have to do. This is your target to meet. And if you don't, then you can play around with like, all right, this is off spec. We send it here, we send it there. But yeah, in terms of the water quality, we're seeing like this one water, it's going to be high quality.
Thanks, you guys. And
Thanks, Kat.
We wanted to say that you can both of you have some ASCE granted charges that we're in.
all right, can we get the attendance numbers for today?
Yes, we have a total of
10 virtual participants and 3 in person for a total of 53.
All right, 53 folks. Thank you, everyone. All right, well, our next meeting will be in May, and then we'll have one more in June before we take a break for the summers month, and thank you for coming.